I want to tell you a little bit about trying to do thermodynamics for quantum systems in the limit of strong coupling. So when you have some quantum system that is strongly coupled to the reservoirs, and so the system's dynamics tend to be non-Markovian and all of this sort of thing. So the picture I like to show, but I think we don't need to go further into this, so I can maybe skip a few transparencies, is to say, you know, we all know that generating power at the macroscopic level obeys the laws of thermodynamics. So there's some big power station here that obeys the laws of thermodynamics. And we want to go down to the quantum level and see if the laws of thermodynamics still apply in the context of turning heat into work or work into heat. Okay, so do we still have Carnot efficiency as the upper bound? If so, how do you prove it? And then to go beyond that and to look at, to go beyond, say, the second law of thermodynamics and look at fluctuation theorems. So maybe I can show you the overview. So I want to ask, are the laws of thermodynamics the same in quantum? And everything I'll say, I'll cut to the end. I've not found anything that's different in quantum than in classical. So that's the main message, I guess. But particularly we're interested in strong coupling, where the system is non-Markovian. So we already know in classical systems strong coupling is difficult. So now we have strong coupling plus quantum. And one of the particular things that is common is that the system and the reservoirs are strongly entangled when you have strong coupling. And so often it's not natural to... As a theorist, it's very nice to start with the system decoupled from the reservoirs. That's the thing a lot of people do. But it's not necessarily natural when you're in strong coupling for a real experimental system. So at the end, I hope to say something about when you don't start with the system and the reservoirs in a product state. Okay, so the quick overview is that I'll give a couple of experimental examples. I think we can skip that. I will remind you what fluctuation theorems are, because I think we haven't had yet anyone saying anything about fluctuation theorems. I will mention, for those of you who know this, there's this theory due to Seifert called stochastic thermodynamics. And basically what I want to do is a quantum equivalent of this classical theory, which is stochastic thermodynamics. So it is my crutch at each step in the calculation. I say, well, what would he do? And I go to his review or other reviews and I see what he's done, and I try and do the same thing for quantum systems. And I will use a sort of Keldysh method. Let's start with some experimental examples. So as we've already had a bunch of talk, let me show you the sorts of things I'm thinking about. So I really like this example because there's this very nice experiment where which shows why you might be interested in quantum systems because a photosynthetic molecule that you can take out of any leaf of any plant you like is, well, at least it's a nanoscale system. It's got a lot of chemistry. To what extent is it quantum or not is an issue that's being debated. But what I think is very cute here is if you take one of these molecules out of a leaf and you put it on a metallic substrate, you put an STM tip on it, and then you shine light on it, you can generate an electrical current between the tip and the surface. So this is a really simple example you can give to even non-physicists of a nanoscale or maybe a nanoscale machine that is turning heat into work. And you just need to remember that sunlight is basically heat, it's basically blackbody radiation. So then this is a rather uncontrolled system in the sense we haven't built it, it's nature that's built it, and it's hard to know exactly what's happening. But of course we've had various very interesting simpler models which are built where the Hamiltonian is constructed by hand and do similar things. So the sort of Hamiltonian that you have is the sorts of things we've already seen. We have some Hamiltonian for the small system. You have some Hamiltonian for macroscopic reservoirs. You assume the macroscopic reservoirs have no interactions in them, so it's just a simple, very simple Hamiltonian. And then there's some coupling between the system and each reservoir. So the coupling terms are some complicated things. But the main message I want to get across is that if we want to think about the second law of thermodynamics, the Hamiltonian is not enough. So these details are not what's really important. If you want to calculate things for a given system, of course you need to know these details, but what's really important is to think about what you mean by irreversibility. And that's not contained in the Hamiltonian. So let's go back to Boltzmann. And so Boltzmann postulated that you could, that the laws of thermodynamics could be derived from Newton's laws, when we know Newton's laws are irreversible in time, when the laws of thermodynamics are, Newton's laws are reversible in time, and thermodynamics, there's an arrow of time, things go in a particular direction, entropy increases with time. And so he pointed out that you could derive these things under an additional assumption, physically motivated assumptions, which is you have Newton's laws, but you also have some loss of microscopic information. And the production of entropy comes from the fact that you don't have access to all of the microscopic information in the system. You have access to macroscopic observables. And so the example of his proof was to take some more or less ideal gases, but with some fast relaxation to thermal states within the gases, so you lose the details of what happens and you have to approximate them by thermal states. And that enabled him to use, I've forgotten what it's called, is it H theorem? Yes, okay, H theorem, yes, okay. So of Boltzmann to derive the second law from some more fundamental theory. Which of course was a big shock to people who thought that the second law of thermodynamics was a fundamental theory of nature. Okay, and of course there's a counterexample which caused a lot of discussion and still causes a lot of discussion, which is if you start putting in systems or machines that do know about the microscopic dynamics, then you can quite easily violate the second law. Okay, so that's what Maxwell proposed, and many people, Feynman, Ratchet, and many other things. Some of them work, some of them don't work. I think the suspicion in the community is that if you take into account the energy consumption of the demon to do what he has to do, then the second law comes back, but maybe you won't agree with me. I don't know how many people believe that. It's in simple models, I know how to prove it in a couple of simple models, but I don't know. Yeah, well, you have to make the analogy, use Landauer's principle to make a connection between information and energy, and do it all. Okay, so that's not the subject of this talk. So what's the subject of this talk? The subject of this talk is to try and do something similar for quantum systems. So I'm going to be a little bit more. I'm going to set up a slightly different situation, which is I'm going to assume that. In principle, I have some small quantum system that I can know everything about. Okay? It doesn't matter, so I can in principle know its microscopic states. But then I have macroscopic reservoirs where I'm not allowed to know what's happening at a microscopic level in those big reservoirs. Okay? So it's what I call the assumption that there's no Maxwell demons in the reservoirs. If you're studying the quantum system, with lots of probes, then you can imagine you can get all of that information. If you're decoupled from the system in your experiment, everything I say will still hold. It's just that then what's happening in the system is just a bookkeeping thing for me as a theorist doing my calculation. It doesn't matter if it's actually physically accessible or not, but what's crucial, the crucial assumption is that I'm not allowed to know what's happening microscopically in the reservoirs. And one consequence of that is that I lose all information about correlations between the system and the reservoir. That is not useful. I cannot use that information to generate work. And that means that the right definition of entropy for this system is what most of you would have written down anyway, which is that the total change in entropy is the change in entropy of the system plus the change in entropy of the reservoir. So there's no there's no entropy of entanglement between a system degree of freedom and a reservoir degree of freedom. That's not allowed.
What's the entropy of the system?
So the entropy. So, well, I'll come back to that, but basically it will be the von Neumann entropy. So if it's some n-level system, it will be the von Neumann entropy. It's a recipe from which I managed to prove the second law and some fluctuation theorems. If you don't like my definition, that's completely all right. Maybe you can derive the second law and fluctuation theorems from a different definition, I don't know. But at least in this one, I believe I can do it. So I'm going to stick with this. Okay, so am I doing for time? Okay, so let me just make a diversion. So probably many of you already know what fluctuation theorems are. So this is a little diversion for the people who've never seen a fluctuation theorem. So the thing we notice in everyday life is that if you take a glass, don't worry, I'm not going to, I put a picture so I don't have to break it. If you take a glass and you put a little bit of explosive in it and it explodes, something like this, then that's very natural. That happens, I mean, all the time. If you do that sort of thing, that happens all the time. If, on the other hand, you take the broken glass and you put as much explosives anywhere you like around it in any way you like, you'll probably never get the reverse process. Okay, and of course we all know why that is. We all learned that you can define entropy in terms of, so there's basically one good state, the state where the glass is not broken, and there are millions or tens of millions or even more bad states where the glass is broken. So the entropy change between being good and bad is very large. And so, but then in this very simple example, when you count the number of good and bad states, it's not too hard to prove a trivial fluctuation theorem, but it gives you a flavor of what fluctuation theorems look like. And the trivial fluctuation theorem is that the probability to go from a broken glass to a perfect glass is equal to the probability of the reverse process. So this is of order 1. We know it's easy to break a glass, multiplied by an extremely small exponential factor. And the extremely small exponential factor contains the entropy change in the exponent. And then you look at this, and of course, to derive this, all I did was take the logarithm of the number of states and the probability defined like this, and then the logarithm cancels with the exponent, and it all looks rather trivial. So why would I write it like this? Why would I write it in terms of exponents of logarithms? Well, the reason is because in more complicated systems, you don't need to count the number of microstates to measure the entropy. So the entropy change in some large reservoir of electrons or phonons is just the change in the heat in the reservoir divided by its temperature. Okay, so then you have some complicated machine and there's heat flowing in and out from macroscopic reservoirs, and you never need to worry about counting microstates. You just use this sort of formula for the entropy. So then the entropy becomes a very natural quantity, and then we have all sorts of fluctuation theorems that one can write down. So this one is not completely general. It relies on a particular set of initial and final conditions, which I won't go into, but it's very much like the one on the previous page. So it tells you that the probability that the entropy of the universe goes down by delta S is equal during some random thermal process is equal to the probability that it goes up by delta S multiplied by an exponentially small factor. So this tells you that if you know how much, if you have a distribution of what the probability of an entropy change is for all positive entropy, that completely determines the entropy change for all negative entropies. So the two are not independent of each other. And of course this relies on some conditions, but if you believe Seifert's stochastic thermodynamics, then this relationship is always true. Okay, that the exponential of minus the entropy change averaged over all possible thermal fluctuations is exactly equal to 1. Okay, so either of these, it's not too hard to show that the second law holds on average, but obviously even this one contains a lot more information than this because it's an equality when this is only an inequality. So my main objective is to derive this relationship. And then the second law of thermodynamics will follow. Okay, so that's what I want to say. So I want to do this for as arbitrary a system as possible. So some small quantum system coupled to large non-interacting reservoirs, and that system could have time-dependent driving, could have all sorts of interactions in it, and so on. So there have been various works already on the subject. Quite a few people in the audience will appear on this transparency. So there have been various exact proofs of certain fluctuation theorems, which when I say exact, they rely typically on saying we know that the system plus the reservoirs all obey a Schrödinger equation which evolves, and then using clever tricks you can prove things. That's beautiful, but typically, except in a few very simple cases, it's hard to match that with a calculation of a real power output of a real machine, because typically the solving the system plus the reservoirs is not possible, except in a couple of exactly soluble problems. So I want something where I can match my theory with one in which I can calculate power outputs and efficiencies and all of these things. Then, of course, for weak coupling, many, many things are known. There's often it maps onto things that look more or less like classical rate equations, which are what stochastic thermodynamics already treats. In some cases, when there's coherent superpositions, many other things are also known. But weak coupling means your machine has a small power output. If you have a small probability to tunnel in and out of your little system, it will never generate a very large power. So we want to go beyond weak coupling for very practical, boring engineering reasons. You want to improve the power output of your machine. And then last but not least, a series of beautiful works using Keldysh, which are sufficiently complicated that I struggle to understand them, and I have nothing more to say. As I understand, there's some ambiguities in certain things related to the energy and the coupling between the system and the reservoirs, but maybe I'm not sure what the latest news is on that. I don't know what David would say on that subject, as he's one of the main people, and there's some other people here who also certainly have things to say. But as far as I know, up to now, everything's been done on either non-interacting Hamiltonians or adiabatic driving. So I want to go beyond that. I want to think about fast driving with all sorts of interactions. So I took a different route. So this is Keldysh in the way that Liliana explained. So I'm going to do a different kind of Keldysh, which I think is due to Scholer and Schoen, which is called real-time transport theory, which I think Janine uses. It was hidden behind some of the things you said in the previous talk. Okay, so it's called real-time transport theory, but I don't think it's the fact that it's in real time that is the most important thing for what I want to say. I think what's important is that I treat the system, this small quantum system with n levels, in its many-body eigenbasis. Whereas, as I understand it, all of the works that you guys did, you treat the system in the eigenbasis of individual electrons. And so this makes things, I think, much simpler in my case. So imagine my system is simple enough that I can exactly diagonalize its Hamiltonian with all interactions then in there for free. So that's when the system is not coupled to the reservoirs. The reservoirs in that case are trivial because they're non-interacting particles. So the only problem is to deal with the system reservoir coupling, right? So this is the non-trivial thing. So initially I'm going to assume that I start with the system and the reservoirs in a product state, and then right at the end I will try and remove that assumption. So I don't think you need to worry about the Hamiltonian. So then in real time, you draw diagrams. So we're doing perturbation theory in the coupling between the system, the small system, and the large reservoirs. And so in the small system, because I've exactly diagonalized the Hamiltonian, as a function of time, if there's no interaction with the reservoir, nothing happens. Okay, so the small system as a function of time, up until the first interaction with the reservoir, if it starts in some state A, it stays in some state A. And then at some time, there's a first interaction with a certain mode in a certain reservoir. So this is the Keldysh contour. So there are two lines. One, if you like, is the evolution. If you think in terms of the density matrix, then when you evolve in time, you always put an evolution operator to the left of the density matrix and another one to the right. So what's happening to the left of the density matrix is on the upper line, and what's happening to the right is on the lower line. So it's a formal way of saying that. These interactions are relatively easy to deal with because at each moment in time, the system is only interacting with one reservoir mode. So it reduces to something that's more or less Markovian, and it's the sequential tunneling limit for the people who are used to quantum transport. But what, of course, we want to worry about are diagrams where the system is interacting at a certain time, say here, the system is interacting with 3 different reservoir modes, or n, or some arbitrary number. So we want to try and sum up all of these diagrams. And of course, in general, we can't sum up all of these diagrams, but what I want to do is draw attention to a symmetry between the diagrams. Okay, so how am I doing for time? Did I start did I start? I didn't pay attention. Pardon? Sorry? 10 minutes. Okay, so then I'll make a very short detour. So this work has been what I would call slow science. I had the basic idea about 2 years ago, and I sent it off to, very excited, to the review to be refereed about 18 months ago. And I had 2 really good referees, so maybe they're in the room, so I may want to thank you, who said, whoa, slow down. And they're right, okay? And they said, okay, you've got this result, but there's a lot of things to build a theory, you need more than just one formula. So I'll show you the one formula I had. But first you need to check all of the basic things. And given all of the confusion, all of the subtleties in the other Keldysh theories, the referees quite rightly said, but what happens about energy conservation? What happens about the first law? So I think probably I don't want to go into details in the time I have. I just want to mention, if anyone wants to know about the first law of thermodynamics, to calculate the total energy, you can calculate some sets of diagrams which are well known or in the papers of Scholler and Schoen. And then you get the first law. You can separate things into heat in the reservoir, work in the reservoir, work that's been done by the drive. The total energy is obviously the change in the total energy is equal to 0 because you have energy conservation. And so then there's a term here which is the change in energy in the system plus the coupling between the system and the reservoirs. Okay, so in the trivial case that we all think about in our first course on thermodynamics, where the system goes around a cycle and returns to its initial state, then if that's the case for the system plus the coupling between the system and the reservoirs, then this term is 0, and you just have the usual thing that work generated is equal to heat absorbed. So it's the first law. And if not, if this is non-zero, it means you're using the system as some sort of battery. You're changing the amount of energy that's in the system or in the system reservoir coupling. Okay, so now now let me come back to what I said. So I'm sticking with the idea that my entropy change is the entropy change of the system and the entropy change of the reservoirs. The entropy change of the reservoirs is just given by Clausius, and I'm going to say the entropy change of the system, degrees of freedom, is just the von Neumann, or let's say the entropy of the system is given by its von Neumann entropy. So that means you need to take the system density matrix to its diagonal basis and calculate the von Neumann entropy, and then the change in the system entropy between the beginning and the end of the evolution is just the difference in its von Neumann entropies. This is the standard formulation from classical stochastic thermodynamics. And then,
Can you go back a second? This assumption about the reservoirs already encapsulate a bit of weak coupling in it, no? Because if you say the delta S of the reservoir is really the von Neumann, then this is true only if you change a little bit the reservoir. If you change it significantly, as can happen in strong coupling, then there's another relative entropy term, and so on. So I don't know if this matters.
Yeah. So it may depend what you mean by strong coupling. I'm assuming that the reservoir is truly infinite, so that the proportion of modes in the reservoir that I change, I drive them far from me. I can, each time an electron comes out of my system and goes into the reservoir, that drives that reservoir mode far from equilibrium. But there are so many reservoir modes that I will never interact with that reservoir mode again. So that's not the same as if the reservoir is somehow finite. So there are some subtle issues. I agree that there's some subtle issues about what strong coupling means. So I think I can defend it for my particular choices, but I'm not sure it's the only choice you could make. And now we come to the central result, which is the one I had and I was all excited about, which is that if you take some arbitrary diagram going from time t0 to time t, then you can write down a time reverse of this diagram. The time reverse of this diagram, of course, you should switch around in time, but when you think about it for a second, you should also switch around these two lines. So what it does, the time reverse of a diagram, is to rotate the diagram by 180 degrees. And so this is my picture of the same diagram rotated by 180 degrees. And there's this equality between the two, which is the weight of this diagram and the weight of its time reverse is the same up to a factor of this entropy change. So this looks very much like the first fluctuation theorem I told you, but now it's on the Keldysh contour, blah, blah, blah. And this looks very much like a similar relationship which appears for trajectories in stochastic thermodynamics and is the central building block of the derivation of all of the fluctuation theorems and the second law and all of these things in classical stochastic thermodynamics. So I'm very happy. So I think I'm on the way to deriving these fluctuation theorems, and indeed it seems like it works. It seems like you then plug this object into a set of steps that look exactly the same as in the classical stochastic thermodynamics, and you get out the right results. The subtle issue is that you have to time reverse all of the states, which is not so trivial in quantum mechanics. I'd forgotten how to do it, but it's all in Messiah's textbook. And for spins, time reversing states is really complicated. I'd need the textbook in front of me to explain it to you, but never mind. But the basic idea for the relationship is that if I take the upper line is a bracket of between the initial state, a set of operators, and the final state, and the lower line is a bracket between an initial state, a set of operators, and the lower state. If I take those two brackets and I switch them around, I basically get this diagram. Okay, so there's lots of subtleties, but that's the basic thing. You can either write a bracket of two objects like this or like this. They're going to be equal up to, when you're careful, a factor that is the entropy change in the reservoirs. Okay, good. So now, and so then that's the first ingredient. The second ingredient you steal from stochastic thermodynamics with this definition of the entropy change, and then you do the same algebra as in stochastic thermodynamics, and you get this fluctuation theorem. You get the second law directly from this fluctuation theorem. So this is always true for any initial product state between the system and the environment. Under certain conditions, you can also get other fluctuation theorems. So what I really like about this is that you can, because it has a microscopic origin, you can make approximations, and you know if the approximation you make will break the second law or not. Okay? So standard approximations are sequential tunneling approximation, co-tunneling approximation. So what I claim is if your approximation contains a time reverse for every trajectory, and it conserves probability, then you should get the exact fluctuation theorems, even though your theory is only approximate. So that's the case if you take sequential tunneling, which is almost Markovian. If you go to next order, you take co-tunneling, then it should still hold. If you go to higher orders, order by order. If you have more sophisticated approximations, I don't know. You have to tell me what they are and check if they obey these rules. Okay, so I just mentioned that you can do the same thing for non-factorized initial states in actually a rather trivial way, which is just to say the standard thing. I imagine that some long time in the past, my system was in a product state between the system and the reservoirs. And I have a fluctuation theorem that I've proven between that long time in the past and the time t1. I can take another system that was prepared in the same state a long time in the past in a product state and instead evolve it forward not to time t1 but to time t2. It will obey a fluctuation relation, a fluctuation theorem, and then with a little bit of algebra I can show that that means the change of entropy between the time t1 and the time t2 has some distribution, and if you average over that distribution you also get this relationship. So you also get the second law even if your time at which you start is not the time at which the system was in a product state. And I think that's everything I wanted to say, so sorry if I took a little too long. So I think we can get fluctuation theorems for arbitrary quantum systems and also for a family of well-known approximations. And so that should give you confidence that if you make some approximation, if you violate the second law, it's not a problem in the approximation you made, it's a problem in your code that you wrote, or you've made a sign error in a formula somewhere. It's not a fundamental problem of the approximation, at least if you use the approximations with a good behavior. Okay, thank you.